The allure of Mars has captivated humanity for centuries, drawing the curious and the adventurous to ponder its mysteries. Its rusty red surface, visible even to the naked eye, whispers tales of ancient waters and the possibility of past life, sparking imaginations and scientific inquiries alike. Today, NASA stands at the forefront of turning this age-old dream of reaching Mars into a reality, with dedicated teams working tirelessly to overcome the myriad challenges. Their ambition extends beyond simply reaching Mars. They aim to unlock its secrets and pave the way for future generations. They envision a future where humans will walk on its surface, explore its mysteries, and perhaps even establish a permanent presence, creating a new chapter in human history. However, the journey to Mars is not a simple feat. It requires overcoming numerous technical and logistical hurdles. The red planet, at its closest, lies roughly 34 million miles from Earth, a distance that presents a formidable challenge. This vast distance presents a formidable challenge, especially given the limitations of current chemical rocket technology, which has been the backbone of space travel for decades. Traditional rockets, reliant on chemical reactions for thrust, require immense amounts of fuel, making the journey long and arduous, and posing significant logistical challenges. A typical one-way trip to Mars using conventional spacecraft would take around 7 months, a duration fraught with potential hazards. This extended travel time poses significant challenges for astronauts, including exposure to cosmic radiation, psychological strain from prolonged confinement, and the logistical complexities of carrying sufficient supplies to sustain life. The dream of reaching Mars hinges on our ability to overcome this fundamental hurdle of travel time, which is critical for the safety and success of the mission. We need a propulsion system that is both powerful and efficient, capable of shortening the journey and mitigating the risks associated with prolonged spaceflight, ensuring a safer passage for astronauts. This is where nuclear thermal propulsion emerges as a beacon of hope, a potential game-changer in our quest to explore the red planet and beyond, offering a promising solution to the challenges of interplanetary travel. Nuclear thermal propulsion, or NTP, represents a radical departure from traditional chemical rockets. While chemical rockets derive their power from the energy released through chemical reactions, NTP harnesses the immense energy stored within the atom itself. At its core, NTP relies on a process called nuclear fission, where the nucleus of a heavy atom, typically uranium, is split apart, releasing an extraordinary amount of energy in the form of heat. Here's how it works. A nuclear reactor forms the heart of an NTP system. Within this reactor, carefully controlled fission reactions generate intense heat. This heat is then used to energize a propellant, usually hydrogen, which is pumped through the reactor core. The hydrogen, heated to extreme temperatures, expands rapidly, and is expelled through a nozzle at high velocity, creating thrust. This mechanism gives NTP a significant advantage over chemical rockets. The energy density of nuclear fuel is vastly greater than that of chemical propellants. This means an NTP system can generate significantly more thrust for a given amount of fuel, enabling shorter travel times and larger payloads. The benefits of NTP extend far beyond just raw power. Its inherent advantages make it an ideal candidate for deep space missions, particularly to Mars and beyond. Higher thrust-to-weight ratio. NTP engines boast a significantly higher thrust-to-weight ratio compared to their chemical counterparts. This means they can achieve higher speeds using less fuel, making them ideal for traversing the vast distances of space. Improved efficiency. NTP systems are remarkably efficient in converting nuclear energy into propulsive power. This translates to shorter travel times and reduced fuel requirements, significantly impacting mission costs and complexity. Reduced transit time. The higher efficiency and thrust of NTP could potentially cut the travel time to Mars by half, reducing astronaut exposure to radiation and other spaceflight hazards. A faster transit also allows for more frequent launch windows and greater mission flexibility. Enhanced payload capacity. With less fuel needed for propulsion, NTP spacecraft can accommodate larger payloads, enabling more ambitious scientific endeavors and potentially even transporting the infrastructure needed for establishing a human presence on Mars. These advantages make NTP a compelling solution for overcoming the limitations of conventional rockets, paving the way for a new era of deep space exploration. Section 4. A Legacy of Innovation, the History and Evolution of NTP. The concept of nuclear propulsion emerged in the early days of the space race. Both the United States and the Soviet Union recognized its potential, leading to parallel research efforts during the Cold War. In the United States, the Rover program, initiated in the 1950s, explored various nuclear rocket concepts, culminating in the development of the NERVA, or Nuclear Engine for Rocket Vehicle Applications, engine. NERVA represented a significant leap forward in NTP technology. It demonstrated the feasibility of a nuclear thermal rocket, proving its ability to generate substantial thrust and withstand the extreme temperatures and pressures involved. However, the program was ultimately canceled in 1972 due to shifting political priorities and concerns about the environmental impact of nuclear testing. Despite the setback, interest in NTP has recently been reignited. NASA, in collaboration with private companies, has embarked on new initiatives to revive this promising technology. One such project is the DRACO, or Demonstration Rocket for Agile Cislunar Operations program, which aims to develop and test a nuclear thermal propulsion system for missions to the Moon and Mars. Section 5. Forging the heart of the engine. Designing the NTP reactor core. Designing a nuclear thermal rocket engine presents a formidable engineering challenge, particularly when it comes to the reactor core. This core is not just any component, it is the very heart of the engine, the powerhouse that drives the entire system. This critical component lies at the heart of the NTP system, responsible for initiating and controlling the nuclear reactions that generate the immense heat needed for propulsion. Without a well-designed core, the engine simply cannot function. The reactor core must be capable of withstanding extreme temperatures, often exceeding 2,500 degrees Celsius, while maintaining structural integrity and preventing the release of radioactive material. This is no small feat, as the materials used must endure these conditions without degrading. This demands the use of advanced materials capable of enduring such harsh conditions, such as high-temperature ceramics and refractory metals. These materials are specially engineered to resist melting and maintain their strength at high temperatures. Furthermore, the core design must ensure efficient heat transfer from the nuclear fuel to the propellant. This is crucial for the engine's performance, as efficient heat transfer directly impacts the thrust and efficiency of the rocket. This involves optimizing the geometry and composition of the fuel elements and the flow channels for the propellant, ensuring maximum heat absorption and minimal pressure drop. The design must balance these factors to achieve optimal performance. Another crucial aspect is criticality control, which involves regulating the rate of nuclear fission within the core to maintain a stable and predictable power output. This stability is essential for the safe and efficient operation of the engine. This typically involves the use of control rods made of neutron-absorbing materials, which can be inserted or withdrawn from the core to adjust the rate of the nuclear chain reaction. These control rods are vital for maintaining the delicate balance required for sustained nuclear reactions. Section 6. Precision in every atom, performance metrics and material challenges. The success of an NTP system hinges on achieving optimal performance across a range of critical metrics. These metrics are essential for ensuring the engine operates efficiently and effectively in the harsh environment of space. Thrust. The core design plays a pivotal role in determining the overall thrust generated by the engine. This thrust is what propels the spacecraft forward, making it a fundamental aspect of the engine's performance. Optimizing fuel distribution, flow channels, and heat transfer mechanisms is crucial for maximizing thrust output. Engineers must meticulously design these systems to ensure that every drop of fuel is used efficiently. Specific impulse. This metric measures the efficiency of the engine in converting propellant mass into thrust. A higher specific impulse indicates a more efficient engine, which is vital for long-duration space missions. A higher specific impulse translates to more efficient fuel use and longer mission durations. This efficiency is critical for missions that aim to explore distant planets or travel beyond our solar system. Fuel burnup. Maximizing the amount of nuclear fuel consumed during operation is essential for mission efficiency. Efficient fuel burnup ensures that the engine can operate for extended periods without needing frequent refueling. The core design must facilitate efficient fuel burnup to minimize waste and extend the operational life of the engine. This involves advanced engineering techniques and precise control over the reactor's conditions. Material science plays a critical role in addressing these challenges. The materials used in the engine must withstand extreme temperatures and radiation while maintaining their structural integrity. Researchers are constantly seeking new materials and fabrication techniques to improve the performance and durability of NTP components. This ongoing research is crucial for the advancement of space travel technology. High-temperature ceramics, for example, offer excellent heat resistance but can be brittle, making them challenging to use in certain applications. While refractory metals provide strength but are susceptible to corrosion at high temperatures. This corrosion can significantly impact the engine's performance and longevity. Finding the right balance of properties is crucial. Engineers and scientists must work together to develop materials that can withstand the harsh conditions of space travel. Scientists are exploring novel alloys, composites, and manufacturing processes to develop materials capable of withstanding the extreme conditions within an NTP reactor core, while maintaining the necessary structural integrity and performance characteristics. This research is paving the way for the next generation of space exploration.